Good afternoon, students. Today's topic for discussion is on IO devices. So, the topic for discussion is interrupts and handling multiple IO devices. So, interrupting mechanism and the IO device mechanism. How do we handle these IO devices? So, that today's lecture objectives are that this session will develop the students' knowledge on how to we perform multiple tasks using IO devices. So, interrupts. So, during IO operations, processor is in waiting until the required data is ready. To overcome this, IO device can send an alert in the form of a hardware signal, which is called it as an interrupt request to the processor. The routine executed in response to an interrupt request is generally called it as interrupt service routine. So the interrupts are like this basically. For example, you have a computer program 1, so which is a compute routine we are calling it as. So the instructions are like this: instruction 1, instruction 2, and so on. The ith instruction and then I plus 1. Like that we have so and so instructions, which are m number of instructions are there. So normally the instructions are executed in a sequential manner. First instruction is executed, then second instruction. Like that, it will continue the execution of the instructions till ith instruction. For example, this ith instruction is related to some interrupt. So that means this ith instruction is generated some interrupt. Then what it does is that the control will be transferred to the another routine, which we can call it as the a display routine. For example, this may be an output statement. The ith instruction may be an output instruction, which is used for displaying something onto the screen. Then it will generate an interrupt to the display device, and then it will jump the control to the display device so that the display routine will be executed, so that it will perform this set of operations to display that character onto the screen. So once the display operation is over, it will come back to the next instruction in this program 1, I plus 1 instruction, and it will continue its execution. So this is what we are calling it as some instructions in the program may generate some sort of interrupt. Once the interrupt is generated, there is a interrupt service routine will be there to provide the service to the corresponding interrupt. So assume that an interrupt request arrives during the execution of an instruction I. The processor first completes the execution of the instruction I, then it loads the program counter with the address of the first instruction of the interrupt service routine. So after execution of the interrupt service routine, the processor returns to the instruction I plus 1. So therefore, when an interrupt occurs, the current contents of the PC, which points to instruction I plus 1, must be put in temporary storage in a known location. So a return from interrupt instruction at the end of the interrupt service routine reloads the PC that temporary storage location, causing the execution to resume at an instruction I plus 1. So the PC has to be loaded once the interrupt service routine execution is completed, because it has to continue the main program execution from I plus 1 instruction onwards. So the return address must be saved either in a designated general purpose register or on the process stack. So the processor must inform the device that its request has been recognized so that it may remove its interrupt request signal. So this can be accomplished by means of a special control signal called interrupt acknowledgement, so which is sent to the device through the interconnection network. So the task of saving and restoring information can be done automatically by the processor or by program instructions. So the process of saving and restoring registers involves memory transfers that increase the total execution time. Hence, represents execution overhead. So saving registers also increase the delay between the time in an interrupt request is received and the start of execution of the interrupt service routine. So this delay is called it as interrupt latency. This delay is generally called interrupt latency, we can call it as. So now the reflection point is that what is the difference between interrupts and subroutines? So how do we enable and disabling of interrupts? So the interrupts can be enabled. Okay, how we can enable these interrupts and disabling of the interrupt? So it is convenient to be able to enable and disable interrupts at both the processor and IO device ends. So the processor can either accept or ignore interrupt requests. An IO device can either be allowed to raise an interrupt request or prevented from doing so. A commonly used mechanism to achieve this is to use some control bits in the registers that can be accessed by program instructions. So the processor has a status register which contains information about its current state of operation. Let one bit, which is called it as IE, of this register be assigned for enabling and disabling of interrupts. So this is a status register is there, PS is a status register will there. In that status register, one bit IE will be taken to enabling or disabling of these interrupts. So thus the programmer can set or clear IE to cause the desired action. When IE is equal to 1, interrupt requests from IO devices are accepted and serviced by the processor. When I is equal to 0, when IE equal to 0, the process simply ignores all interrupt requests from IO devices. So this is how we are making use of IO flag bit in the status register, whether the processor has to attempt the interrupt servicing or not. So the interface of an IO device includes a control register that contains the information that governs the mode of operation of the device. So one bit in this register may be dedicated to interrupt control. So the IO device is allowed to raise interrupt requests only when this bit is set to 1. So sequence of events involved in handling an interrupt request from a single device. So the device raises an interrupt request, the processor interrupts the program currently being executed and saves the contents of the PC and PS registers. Interrupts are disabled by clearing the IE bit in the PS to 0. The action requested by the interrupt is performed by the interrupt service routine, during which time the device is informed that its request has been recognized, and in response it deactivates the interrupt request signal. Upon completion of the interrupt service routine, the saved contents of the PC and PS registers are restored. That means we are enabling interrupts by setting the IE bit to 1 and execution of the interrupted program. Then how do we handle multiple devices? So let us consider now the situation where a number of devices capable of initiating interrupts are connected to the processor. How can the processor determines which device is requesting an interrupt? Given that different devices are likely to require different interrupt service routines, how can the processor obtain the starting address of the appropriate routine in each case? Should a device be allowed to interrupt the processor while another interrupt is being serviced? How should two or more simultaneous interrupt requests be handled? So if two devices raise interrupt requests at the same time, it must be possible to break the tie and select one of the two requests for service. So when the interrupt service routine for the selected device has been completed, the second request can be serviced. So when the device raises an interrupt request, it sets to 1 a bit in its status register. That is, IQR bit is set. The simplest way to identify the interrupting device is to have the interrupt service routine poll all IO devices in the system. So the first device encountered with its IQR bit set to 1 is the device that should be serviced. An appropriate subroutine is then called to provide the requested service. So for that we are providing a mechanism or a method called it as a vectored interrupts mechanism. A device requesting an interrupt can identify itself if it has its own interrupt request signal or if it can send a special code to the processor through the interconnection network. The processor circuits determine the memory address of the required interrupt service routine. So a commonly used scheme is to allocate permanently an area in the memory to hold the addresses of interrupt service routines. These addresses are usually referred to as interrupt vectors and they are said to be constitute the interrupt vector table. IO devices should be organized in a priority structure. An interrupt request from a higher priority device should be accepted while the processor is servicing a request from a lower priority device. So a multiple level priority organization means that during execution of an interrupt service routine, so interrupt requests will be accepted from some input devices but not from others depending upon the device priority. So to implement this scheme, we can assign a priority level to the processor that can be changed under program control. The priority level of the processor is the priority of the program that is currently being used. The processor accepts interrupts only from the devices that have the priorities higher than its own. At the time that execution of the interrupt service routine for some device is started, the priority of the processor is raised to that of the device either automatically or with the special instructions. So this action disables interrupts from devices that have the same or lower level of priority. However, interrupt requests from higher priority devices will continue to be accepted. So the processor's priority can be encoded in a few bits of the processor status register. So while this scheme is used in some processors, we will use a simpler scheme in later examples. So finally, we should point out that if nested interrupts are allowed, then each interrupt service routine must save on the stack and the saved contents of the program counter and the status register. So this has to be done before the interrupt service routine enables nesting of by setting the IE bit in the status register to 1. So this is what the lecture outcome. After completion of this session, you will be able to perform multiple tasks using IO devices. So thank you one and all.